everyone, I am Valerie from Group 5 and I am here to discuss about our topic in the lesson 16 entitled Torque and Two Conditions of Equilibrium. When you hear the word equilibrium, what comes first to your mind? Yeah, it's the balance, right? But in physics, equilibrium is a state in which opposing forces or influences are balanced. And when we say torque, it is the rotational equivalent of linear force. So an example of equilibrium is when hot air and cold air are entering the room at the same time so that the overall temperature of the room does not change at all. So in physics, there are three types of equilibrium: the stable, unstable, and neutral. So a particle is in equilibrium if it does not accelerate in an inertial frame of reference, if the vector sum of all the forces acting in the principle is zero. For an extended body, the equivalent statement is that the center of mass of the body has zero acceleration, is the vector of sum of all external forces acting in the body is zero. This is often called the first condition of equilibrium. So, a second condition for extended body to be equilibrium is that the body must have no tendency to rotate. A rigid body is in equilibrium can have the tendency to start rotating about any point, so the sum of external torques must be zero about any point. So the next clip will be my group mates to discuss to you further about this topic and to present to you some formulas and problem. So listen carefully because afterward we'll give you an evaluation.
Hello everyone, I am Jim Nicole Bitancor from Group 5. And also our topic for today is all about torque equilibrium.
Hi guys, I'm Kevin Marson of Group 5. Our topic is all about torque and two conditions of equilibrium. In my case, I will give you the problem and provide the answer key. Just watch our video and listen carefully, and I hope you can learn about our topic and understand each problem. And thank you.
Okay, before we solve problem, let me explain the direction of torque. Torque, it has a vector quantity, therefore it has direction. If clockwise, if the rotation is clockwise, so the torque is negative. But if the rotation is counterclockwise, the torque is positive. Let me explain why. If for example you have here a wood and then the fulcrum is at the center, then you exert a force at this point. Take note that we have torque if d sine theta, but if sine is 90, that is equal to 1. So that is just if d, we have here the forces is downward. But the lever arm, the d is positive. And if you're going to push this, the rotation will be clockwise. Negative times positive, that's a negative torque. Another illustration is this. If again you have at the center of the axis of rotation and then the force is exerted here, it's like you're pulling it upward. Now you can see here at the force is positive, but the lever arm is negative. And then if you're going to pull it, the rotation again will be clockwise. So that means there is a negative torque. Now take note that if you have a clockwise rotation, that's a negative torque. And then for the explanation for the counterclockwise torque, we have here. Okay, again, the center is here, or the axis of rotation is at the center. And then you have a downward force here. You can see that the force is negative because it's downward, but the lever arm is negative. You will have a positive torque. Okay, you have a positive torque, which is the rotation is here. You can see that it's in a counterclockwise direction. Another illustration is this. You have here at the center, and then this one, you try to push it upwards. Now, if you will pull it upward, you will see that the rotation again is counterclockwise. The force is positive. The lever arm is positive. Therefore, you have a positive torque. Okay, and that rotation is counterclockwise, so that is a positive torque. Okay? Now, let's try to solve. Okay, let me also discuss about the second condition of equilibrium. In the first topic that we had the first condition of equilibrium, wherein the summation of forces is equal to 0. But for the second condition of equilibrium, the summation of torque is equal to 0. So a positive torque, the torque on one side is equal to torque on the other side, so that they will sum up to 0. That is the second condition of equilibrium, wherein we are going to apply in the next problems.
5 problems with solution and providing answer key.
The woman mass M sits on the left end of the seesaw. The man mass M sits where the seesaw will be balanced. Apply the second condition of equilibrium and solve for the unknown distance x. And now let's have a solution. As I said, torque 1 is equals to torque 2. And also let's provide that the mass of the girl is 40 kilogram and the mass of the boy is 55 kilogram. So the formula is open force 1 to distance 1 equals force 2 and distance 2, 1 over force 2. So the solution is distance 2 equals force 1 and distance 1 equals to force 2. So the force 1 is 40 kilogram times the center of the gravity is 9.8 times 2, and force 2 is 55 kilogram times the center of the gravity is 9.8. So let's calculate. Answer of the distance of 2 is 1.45 mass. These are the distance of the unknown x between the center of the gravity and the boy set aside. Calculate the force that the bicep muscle exerts to hold up the forearm and the book shown in the figure. Compare the force exerted by the bicep muscle with the width of the forearm and the book. And now let's make a solution. The rotation of the bicep is torque counterclockwise equals torque clockwise, and the formula is force of the bicep, distance of the bicep equals force of the center of the gravity and the distance of center of the gravity plus force of the physics book and distance of the physics books, and 1 over distance of the physics books. And the solution is force of the bicep equals open 2.5 times 9.8 times 0.16 over plus 4 9.8 and 0.38. 1 over 0.04. So, let's calculate. 2.5 times 9.8 times 0.16 equals, and 4 times 9.8 times 0.38 equals, the force of the bicep is equals to 470 Newton. And also the force of the load is equals to 63.7 N. These are the solution of the load. 4 times 9.8 plus 2.5 times 9.8 equals 63.7 Newton. So the bicep muscle has the exert great amount of the force, so they can balance it. Calculate the force exerted by the extensor muscle in the upper leg when lifting a weight as shown in the figure. In that image, the rotation of the muscle in the upper leg when lifting a weight is torque counterclockwise equals torque clockwise, and the formula is force mass and distance mass equals torque distance the weight, or force mass equals torque distance with 1 over the distance of the mass. So let's proceed the solution. Force mass equals 10 times 9.8 times 0.35 m divide 0.02. So let's calculate. 10 times 9.8 times 0.35 equals divide 0.02 equals, the answer is 1715 newtons. That's the force exerted by the extension muscle so that it will be balanced, or so that there will be no rotation. Even when the head is held erect, its center of gravity is not directly over its major point of support. The atlanto-occipital joint, the splenius muscle in the back of the neck, must therefore exert a force to keep the head erect. Calculate the force they must exert if the mass of the head is 5.0 kg. And now let's proceed to the solution. The rotation of the splenius muscle is torque counterclockwise equals torque clockwise, and the formula is force mass distance mass equals force of the center of the gravity and distance of the center of the gravity. Force mass equals force of the center of the gravity and the distance of center of gravity divide distance of the mass. So let's calculate. Was 50 Newton times 0.025 mass divide 0.05. So let's now calculate the force of the mass. 50 times 0.25 divide 0.05. So the force of the mass is 25 Newton.
In the figure, a pole vaulter carries a 6.0 mass long pole by pushing down with his right hand and up with his left hand. The pole is uniform and has a mass of 10 kg. Find the forces at left and right. Next, let's do the solution. Is torque counterclockwise is equal to torque clockwise. Force right, distance right is equal to force with and distance of the center of the gravity. Force right is equals to force with and distance of the center of the gravity divided of the distance right. Force right is equals to 10 times 98 times 2 mass divided to 0.7 mass. Force right is equals to 280 Newton. Next is for the left. Torque counterclockwise is equals to torque clockwise. Force left, distance left is equals to force right, distance right plus force of the center of the gravity and distance of the center of the gravity times 1 over distance left. (280) times 0.3 plus 10 times 9.8 times 3 over 1.0. Force left is equals to 378 Newton.
Niggas in my grill tryna phase me.